I believe I'm audible. आज तो क्लास अच्छी भरी हुई है. Okay, so the delay that we had, the good thing is there is not much to review from the previous class. You've already seen the answer scripts now, and things are clear. Am I right? So today what we are going to do? Cache subsystem design. So why do we need caches? What is a cache? Putting faster memory closer to the processor.
Performance gap between the processor speeds that we have and the memory speeds that we have, and also we have to optimize for a better performance.
So, see, one thing that we have to acknowledge is that because of technology scaling, logic performance has improved tremendously. However, while the logic performance has improved tremendously, the memory performance has not improved in the same way. What could be the reasons for that? How many of you have started your project work? Okay. So now you should be able to tell, agar project work shuru kar diya, you should be able to tell why is the memory performance not scaling as we thought it should.
Could it be because memories are off-chip, so you'll have certain limitations?
Are you designing off-chip memories? No, you're designing memories which are going to sit next to the processor only.
And when we scale it, so the charge stored on the capacitor will be less, but the scale will be somehow similar to earlier. So we'll need much more refreshes.
Okay. So he's saying that main memory is a DRAM, which is off-chip, and it would not be able to do what? It will not be able to what? It will require more refreshes, so there will be. मतलब ये DRAM के कुछ concept लेकर आ गया, बता रहा है कि मैंने पढ़ लिया DRAM वाला section भी, but नहीं. Okay, there's something that DRAMs will have more unavailability, and therefore there will be more longer waits and everything. What else? Let's say I'm talking about SRAMs only. Let's say I'm talking about on-chip SRAMs also. Why would on-chip SRAM's performance not scale in line with logic?
CMOS technology has labs that and modified that CMOS technology, and we have used it in such a way that we can't scale it the way CMOS technology is.
So she's also guessing something. She's saying that we are not using CMOS in memory cell. When you say logic performance has improved, that is the CMOS logic performance has improved, but memory cell is not CMOS logic. And there could be something behind it. She doesn't know the reason why, but she says, kuch to hoga uski wajah se. This must be the reason. Any other guesswork? I'm happy with guesswork because that is where you start to become creative. And guesswork need not always be correct. Have I ever complained that galat bol rahe ho? Jab galat bolte ho, I just tell you what is right. Have I ever scolded you for giving me a wrong answer? So whatever comes to your mind, why do you think memory performance does not scale in line with logic performance?
But like as we go to smaller economy, the impact of mismatching too much, so we cannot make it very small.
Okay, Ria is saying that because there are circuits in the memory which require structural matching and reduced mismatch, as we scale in technology, impact of mismatch is only going to increase. Therefore, you can't really scale performance as much. Okay, what else? In the processor, we apply the Moore's law every time. Oh, in memories also, we reduce the size of the memory cell by half every time.
Not that much. Not in the same time.
So See, in memories also, if you scale from one technology to another, the target for the technology team is that the memory area should go to half. But to be able to take it to go to half, you also have to handle these PR ratios and CR ratios. You have to handle stability, writability, so many things. That was why I asked how many of you started work on your projects. So if you started work on your projects, you know what a pain it is to just design even in 65 nanometer. To handle that, okay, stability should be there, performance should be there, this should be there, that should be there, all those things, it's just a nightmare to design. So what happens is that in the, and this is where your point that it is not a CMOS circuit. Because it is not a CMOS circuit, so many figures of merit are there. Because it is not a CMOS circuit, you cannot simply say, okay, stability is guaranteed. You cannot say that, okay, there is no noise challenge there. There is a lot of risk because of noise, because it is not a CMOS circuit. So all these reasons combine, and then that mismatch point also figures in. That sense amplifier offset doesn't seem to be reducing. It only increases with every technology. So where you thought that you will be gaining performance, now your sense amplifier requires more offset. So your bit cell whose current has reduced now has to create a larger differential. And therefore, performance doesn't scale. So what happens is that as you move from one technology to another, even when you have, say, okay, so where we started with, okay, main memory is DRAM, and DRAM is not able to gain that much performance as as logic. That point is very, very valid. Why does DRAM not gain performance as much? Forget about what the DRAM intrinsic performance is. The fact that you have to go out of the chip onto the PCB, then to the memory chip, collect data from there and come back. Even if you scale DRAM performance, majority of the delay is the bridge between the PCB and this and your processor. So it's simply that will not scale. Okay. Now in advanced technologies, as we are looking at it, we're talking about 3D packaging, and that is where packaging is a very, very important. We had Dr. Ashwini Agarwal come and talk about packaging and everything just, I think, two weeks back. How many of you attended that session? Yeah, so he talked about the importance of packaging today. Because of these packaging technologies, we are able to scale the memory performance tremendously. Not because memory intrinsically has improved, just because now you don't need to go to the PCB. You can directly transfer information from one die to another just by placing them one over the other through silicon vias, or so many ways in which we are now able to connect multiple dies on the same chip. So because that was not there, initially the requirement of a cache started from the fact that DRAM is so far away. Physically also, in terms of timing also. By the time I will get something back from there, I would have to wait ages. So we said, okay, let's put something on chip. On chip, उस समय DRAM technology available ही नहीं थी. So the first only SRAM was available, so caches were only SRAM caches. But now what happened? This was long, long back. This was late 80s, early 90s. We already faced this. But now we are 30 years, 35 years ahead of that. What has happened? क्या उसके बाद cache की requirement खत्म हो गई है? नहीं. What we are observing is that the hierarchy of caches has appeared. There is now L1 cache, L2 cache, L3 cache. And that is the reason why we need to talk about cache subsystem now, not just one cache. Are you getting it? So, जो DRAM वाला example है, जो slide में बोला गया है, that is primarily because that is aged. Okay? That is dated information. You need to understand that the same principle has held. Okay, not to that degree, but has held. Performance of memories has not scaled in line with logic. And because of that is one aspect. Another aspect is because of more integration, which again is an outcome of scaling, you now need larger memories. So if you increase the size of memories, on-chip memories, again, RCs will increase. See, instead of a 1K cross 32 memory, if I ask you to make 2K cross 64 memory, R and C both will increase. Performance is going to go bad. So I also need larger memories. That is another reason why we now have a hierarchy of caches, L1, L2, L3. Are you with me? So, friends, I have now started off this session with an assumption that you have watched the lecture. Is that assumption right? Or are there people who have not watched the lecture despite my very, very strong recommendation in the last class? Anyone who has not watched the lecture, please let me know, because if you have not watched, then अगर मैं इस लेवल से शुरू करूंगा आपको कुछ भी नहीं समझ में आएगा. जिन्होंने लेक्चर देख लिया है उनको कुछ समझ में आ रहा है अभी. Am I right? But if you have not watched the lecture, you will just not get anything. Anyone like that, I can lower the level. Because important thing is to understand it well. What's the point in going to advanced topics if your basic level pe there are questions? All of you have watched the lecture before coming to the class? ये नो होता है, ये हाँ होता है. Who have watched the lecture? Okay. You have not. समझ में आ रहा है? That is fine. If नहीं आएगा तो just raise your hand and ask. So beyond what is there in the book, beyond what is there in the dated slides, it is important to understand that the need for hierarchy exists and is becoming stronger every passing day. Because we need larger memories, because we know that memories have analog elements in it which do not scale in terms of performance, in terms of offset requirements. In fact, their offset requirement may increase. And that is okay. So that is also the reason why there is continuous innovation that is happening in memory design. Because technology doesn't let you scale in performance. The technology doesn't help you improve performance. But the user expectation is performance will improve. That is why you go to hierarchical bit lines. That is why you go to the entire range, write assist, read assist, all those things that we are doing. All that jugglery and circus that we are working on, that we have talked about over the past 10 weeks, 10, 8 weeks, whatever. All that is because of performance of memory not scaling in line with logic. This is also in line with the same philosophy. Okay? So what do? We say that we need something which is closer to memory and closer to the processor, and we are able to access that easily. So what is important to understand is that when I am talking about cache hierarchy, my L1 cache need not be as large as the L2 cache, which need not be as large as the L3 cache or the main memory. And the simple reason behind it is also how our brain works. See, in our brain, in our conscious awareness, we always have only a limited set of things. Do we keep everything on our mind when we are studying or when we are talking to someone? No, when I'm meeting you, I just bring your history, retrieve your history out. And that is what arranges my conversation with any one of you over here. Is it right? So this is called locality of reference. That when I'm working on a Word document, I need the files or I need the instructions linked to Word document. When I'm working on a game, I need instructions around the game there. And when I'm working on either of these two, I'm not worried about what are the instructions for loading the PowerPoint presentation. So that is the locality of context, locality of reference. Another is locality of time, temporal locality. That if I am on first frame of my movie, then in a very high probability, I will now need the second frame, then the third frame, then the fourth frame. Usually people watch movie in one go. time-based. When I am having this, then I will need the next spatial locality, that I will need the next one, and next one. So these locality of references tells me that I need to keep the entire movie close to my processor. Only these set of frames which my processor will need, I need to load first. Are you getting it? So that is the reason why cache system works. If a user or if a hacker comes and violates the locality principle there, your system will simply hang. It will go in a deadlock because it would retrieve something, then it would retrieve the next thing, then it would retrieve the third thing. So आपका जो भी cache की availability की वजह से benefit था, that benefit will be negated. Are you able to see this? Locality of reference is the key principle because of which cache subsystems work. Yes, in many server grade systems, embedded DRAMs are used as level 3 caches. Because DRAM is anyway not as fast as an SRAM, whatever you may do. But you can still use it as a cache, and in many server class systems, they are used.
It is proximity based or
Yes.
basically proximity.
It is not necessary that a cache memory has to be an SRAM. In fact, there are studies about not just DRAMs, we're also talking about phase change memories or RRAMs or others, the emerging memory technologies to be used as level 2 or level 3 caches because they are denser than SRAMs, much denser than SRAMs. Is that okay? So, another aspect is that another aspect of a cache hierarchy is that when you put anything in L1 cache, a copy of it has to be available in L2 cache and L3 cache. It cannot be that there is something in L1 cache, but it is not available in L2 or L3. This is called as the inclusion property. This is extremely important because if you update the content of the L1 cache, you need to update the content of L2 cache and L3 cache and the main memory also at some point of time. But if that content doesn't even exist at the different higher levels of hierarchy, then what will you update? So it will lead to errors. Okay. So inclusion property is another very important principle that you have to be aware of and alert about at any point of time. Now, why are all these discussions important? These are important because some of you may want to go into the streams linked to computer architecture or into even say operating system design or something like that. And then when you are working at those levels of firmware, hardware, software, co-design and all those things, then you have to ensure that आपके algorithm में आप कुछ भी ऐसा ना कर दो जहां पे either of these two properties or these key reasons why cache hierarchy works get violated. Are you with me? So, who will explain the cache operation principle?
Is this true for all levels below in a hierarchy or for all the levels in the hierarchy? Because there may be some processes that right stand the ADR memory, and then if some other processor references the cache.
So देखो जो DRAM के अंदर, so the coprocessor that you need to write into the DRAM, that coprocessor has probably only this one function that it has to access the DRAM. Okay, that is not really doing any processing for you. Okay, that is just handling the state machine of writing into the DRAM. When it comes to a processor for which you actually create a cache hierarchy, then the memory that is closest to the processor all of its contents have to be available in the next level, and all of those contents have to be available in the further levels also. They may not be coherent at all times. Do you understand the term coherence? What does coherence mean? And the content is exactly the same. See, when I say that this address should be available in all the memories, address may be available, but I'm saying they may not be coherent. It may be that in the local copy that you have in L1 cache, the content could be different than the content available in L2 cache. Why and how will this be the case? I'm jumping ahead. Those of you who watched the lecture, you realize I'm jumping ahead. Why and how will this be the case?
If some other process creates the value in, let's say, L2 cache, then it needs to be updated in the L1 cache, but it has the level. So we need cache coherence in that case.
Okay. So it may happen that my write back policy, as defined by my operating system, is such that I will not write back until needed. Because I may have some data which is getting updated every cycle by the processor. So why write back after every cycle? Anyways, this data is going to become old and obsolete in the next cycle. However, when I have a memory crunch and I need to flush out some data, some information from inside my cache, then obviously it means that this particular data is no longer being used, and whatever is the latest value needs to be updated in the other levels of hierarchy. Until the time that higher levels of hierarchy have been updated, there is a mismatch between the contents at different levels. That is one. Another reason was what he pointed out, that when there are multiple processors sharing an L2 cache, so processors will typically have their own captive L1 cache. But L2 cache, it being larger, can be shared across multiple processors because multi-threading aap karte ho. So how many of you, I know all of you have done some level of programming. You know the concept of multi-threading. Am I right? What is done in multi-threading?
So you can have multiple like threads running parallel to each other.
So there are 4 processors. Each processor will run one thread of the same program. Therefore, all the 4 processors may need the similar data or the same locality of data. So L2 cache can be common. Are you able to see this? You launched a program because of multi-threading. It was spread over 4 different processors. And now these 4 processors are working out the same program. They need the same kind of instructions, and they can be made available in same common L2 cache. So L2 cache can be common across multiple processors. Now let us say that we are talking about data cache, and processor 1 updated the contents of one particular address in the cache, L1 cache. This data is to be used by another processor also. If that request comes, then you need to first make the data across L1 cache and L2 cache coherent, and then the data needs to be fetched again from L2 cache into the second processor. Are you able to see this? So there are special memory controllers which are used to ensure coherence of data across different processors and at different levels of hierarchy. So the write back scheme that I was talking about, the delayed write back scheme, when you have multiple processors sharing the same locality of reference, then you will never wait for write back. As soon as you update, the processor would say, okay, update the L2 cache also. Are you getting it? So all these algorithms are embedded into your design. A quick check. How many of you have done the computer architecture course? So this must be ringing the bell with you. Am I right? You must have discussed about all these aspects in the computer architecture course also. For those who have not done, these are all the basics of computer engineering. Not saying computer science or the CSE that we have. Computer engineering is a specialization in EC or EV itself, where we talk about the computer architecture and how to design a computer, not how to write a program. Okay. And if you know how to design a computer, you can also learn how to write a very good program. So good programmers always do coursework on computer engineering. Good designers should also do coursework on computer engineering. So those of you who have not done computer architecture yet, it's a very strong recommendation from my side that please do it. Those of you who have not done courses on operating systems yet, a very strong recommendation that you should do it. Okay, these are important. These are important for you to be able to have a consistent understanding across different levels of abstraction in the design hierarchy.
What's the difference between coherence and inclusion?
Inclusion only means that, okay, inclusion means that when I have retrieved address number 48 from the main memory, and that address number 48 is available in L1 cache, then address 48 has to be made available in L2 cache and L3 cache also. In fact, memory controller, जो co-processor हमने DRAM के लिए बताया, that will bring in the information from main memory, and depending on the way you have programmed that coprocessor, it may write into all the 3 caches simultaneously, or it may write into the L3 cache first, and then you have to trickle it down to L1 cache. Depends on what is the algorithm that you've used. So this is about address. Inclusion is just about that whichever addresses are available in L1 are also available elsewhere. Coherency is about the content at those addresses. Are you getting it? That's the nuance of a difference. People typically get confused in these two. ठीक है, आगे बढ़े. आगे बढ़े क्या, पहले यहां तो देखें. What is happening inside the memory? How do you read?
So, firstly, the processor will send the memory address. So it will contain the tag bits, index bits, and the byte offset. So the index bits will be required to firstly see which cache line or which cache row to access, and then it reads the whole cache line with the tag and data, and then the comparator checks for the requested tag and the stored tag, and if they are matched, so it's a cache hit. If it's not, then it's cache miss, and then it will be.
So if you have a 32-bit processor, your address bus will be 32-bit long. You have 32 bits of address to identify what you want to bring inside the processor. The processor will give an instruction like load address 1. Address 1 is 32 bits. Now, the memory right next to the processor is L1 cache. That memory is only 1K words big. Just 1K words. Agar 1K words हैं, how many address bits are we talking about? 10. आपके पास 32 एड्रेस बिट्स प्रोसेसर ने मांगे थे, आपके पास खाली 10 एड्रेस बिट्स की बस अवेलेबल है. What will you do? So what you say is, okay, I know that only 1K words are available here, but I have a 32-bit address bus. MSBs, 22 MSBs. These 22 MSBs I will store in a separate memory. So I have a particular memory which stores data. So let us say because 32-bit आपका processor है, so you have 32 bits of data stored at a particular location. But along with this data, you also store another piece of information, which are the higher order 22 bits. Are you getting it? So what happens when I give the lower order 10 bits, or when I give the 32-bit address, the lower order 10 bits are used to identify, okay, this particular row. all this information is brought out of the memory. And once it is available, I compare the higher order 22 bits that had come from the processor with this information. I do a kind of a XOR operation. If the two match, I know that the address that my processor wanted to read is available in cache. This particular information I will send back to the processor now. If the two do not match, it means the address that I needed is not available. And if that is not available, what do I need to do? I need to go to the next level of hierarchy. And now, let's say the next level of hierarchy is not 10 bits, say 15 bits addresses. Very big, relatively very big, 32 times bigger. Now, you use 15 bits for the addressing and check the remaining 17 bits for the tag. If it matches, okay, L2 mein hit ho gaya, now just bring the data back to L1. If it doesn't match, you go to the still next level of hierarchy. If there is no other level of hierarchy, you have to go to main memory. Are you able to see this? Is this broad level concept clear? That you cannot store every location of the main memory in your cache. What you do is, you have a larger, so even though your processor is 32-bit, your cache may be larger than 32 bits, or there may be a cache which is the data memory and a tag memory. Tag stores the remaining 22 bits of the address. I'm just अभी कह रहा हूँ वो ब्लॉक और टैग और इंडेक्स पे सभी आते हैं. मैं कह रहा हूँ कि आपको कुछ भी नहीं पता हो, आपका कोई भी और ऑर्गेनाइजेशन नहीं है कैश में. एनी डेटा कैन बी एनीवेयर. एनी डेटा कैन बी एनीवेयर नहीं, यू जस्ट डायरेक्ट मैप्ड कैश है अगर कि भाई I will write at the same location where my LSBs are matching. Then this is what you need to do. Now, suppose आप कहते हो कि नहीं नहीं ऐसे में तो बड़ा constraint होने वाला है. I want to write anywhere inside the memory. Suppose you say this. Then what will you need to do? Then you will need to check every location for all the 32 bits. Your tag size will increase and you have to check every location for all the 32 bits. That is where you call in a CAM, content addressable memory. Because you have 32 bits which you want to match and see in which line, in which particular row, I have the full match. Wherever there is a match, that particular location's contents I will throw out to my processor. Are you able to see this? Huh?
Which tag is referring to which?
Oh, इसके लिए तो you always ensure that whichever address you are writing into a particular location, that content has to be in the same location, the same word location in the other memory. So you can actually, instead of keeping two memories, instead of a 32-bit L1 cache, you have a 64-bit L1 cache then, where all the 64 bits are together.
We are comparing with the MSB 22 bits of the given address, right?
ठीक है, आगे बढ़े. So we need to understand what are, so when we talk of a cache subsystem, we talk about a few key traits or characteristics of that subsystem. Performance is the first one, because all of this jugglery you're doing to gain performance. So access time or speed is the first thing, that is the most important thing why you need cache memories. So that is the first figure of merit. Then comes capacity. how big is the cache memory? Because that tells you how many addresses can you store. If you are going to launch huge, big processes, then you may want to have a larger cache memory. But if you're going to launch small processes only, then you need only small memory, which has the required locality. Then associativity. Associativity is about जो अभी हमने पहले बात करा, कि एक हमने कहा कि कोई भी एड्रेस कहीं भी लिखा जा सकता है. Any address can be written into any location. So you need a content addressable memory to even identify where my address has been written. Another way said that, okay, I will check the last 10 address bits wherever wherever those 10 last bits tell me, that is the only location I have to write my contents. So completely different paradigms. In one case, there is a lot of power and a lot of energy taken up by the content addressable memory because you need to compare every row for valid access. In the other case, there is a risk that suppose I'm running two different programs. Both programs need some contents with the same LSBs. I will enter into a situation that he asks his data to be written there, he asks his data to be written there. And the system is always continuously juggling between getting this data from main memory or higher level of cache and this data from the higher level of cache. So every access is going to get delayed. So what we do is we say that, okay, these 10 LSBs, there are 4 locations where you could, either of the 4 locations, you put the data. So what that means is 4 programs can run in parallel. This is called 4-way associative, 4-way set associative memory. You could do 8-way set associative memory. You could do 2-way set associative memory. The larger the number of sets, the more the number of options you have where you could retrieve the data from higher order of memory, higher level of cache and bring to L1 cache. Are you able to see this? Is this point clear? Is the problem clear? Is the solution also clear? You need set associativity so that you do not enter into a zone where you are just doing a ping pong between two different programs. And in today's technologies and in today's architectures, we anyways have multi-threading, we anyways have multiple programs running in parallel. We know that. Multiprocessing hoti hi hai. So it is important that we have set associative architectures. But if you're designing something which is for very primitive applications, for example, just a small sensor node, then you may, and in small sensor nodes, the power consumption, the area, the cost of the chip would be of very high priority. You may want to go to direct mapped also. And for cases where you require super high performance, you do not even go to set associative. You say that, okay, I will go to fully associative. My any data can go anywhere. Is that okay? So one extreme is direct mapped. LSBs देखा और उसी के हिसाब से one location पे ही आप लिख सकते हो. Second, and the other extreme is fully associative. Any data can go anywhere. And in between the two of them, you have this set associative. So associativity is that parameter that defines how many parallel streams or how many options do you have whenever you retrieve data from main memory into your L1, L2 cache hierarchy.
When you talk about fully associative, so how will we implement that? That suppose it can be stored anywhere. What does that mean? Because then will that depend on the replacement policy, which data that we replace?
So that is where the next thing comes in, actually, replacement policy. So I say that, okay, this particular address has not been accessed for last 500 cycles. This content is most probably no longer needed. I want to replace that whenever the new request comes. Now, this particular address might not be in the same set. as uh, as I need. So if you have a set associative memory, such old addresses could be available in some sets and they're not being replaced. But if you are in a fully associative memory and you're talking about a least recently used replacement policy, then this was the least recently used. So this is thrown out, independent of what address it was. The replacement policies work with set associativity also. For example, you have 4 sets. So anyways, when you bring data from the main memory, you have an option of choosing any of the 4 sets. Which one would you use? So that is what the replacement policy means. Which one would you replace? Are you getting it? So replacement policy is another very key parameter which defines a cache subsystem.
Always it is. Sets have same address or what? Like how the LSP can.
So when we have, so very good question. He's asking, suppose I have a 4-way set associative memory, will all the 4 have the same address? In a 4-way set associative memory, the LSBs would be the same. But there are 4 different sets of MSBs that are possible now. The tags can be different. But LSBs will be the same. Are you getting it? So instead of just one 1K word memory, I have 4 1K word memories. And I can choose which one to write my new data into, depending on the replacement policy that we were just talking about. Is that clear? And then the last and the last feature of a cache subsystem is whether you have a separate hierarchy for data and instructions, or is it unified? Unified means both data and instructions will go into the same cache. So your 4 sets are now shared between instructions and data. Or I have a separate cache hierarchy for instructions, which could be smaller, and a different cache hierarchy for data, which could be much larger. Because instructions, in most of your today's applications, for example, you talk about same instruction run over multiple data. So the instruction is not changing. These are called SIMD instructions. So the instruction is not changing much. But the data needs to be brought in and taken out much more frequently. जितने भी आपके AI algorithms and CNN, DNN, they're all about a lot of same instruction happening over a large amount of data. That is also the reason why we are able to talk about in-memory compute and all those things. But in such a setting, you may say that I have a small instruction cache hierarchy and a much larger data hierarchy, because instructions at least can come in very quickly. Are you getting it? So that is the last feature of a cache subsystem that you need to clearly define when you are designing one cache subsystem. So what does access time mean? Access time means in how much time will I be able to get data once the processor requests for it. And if you look at the formula, it's pretty intuitive there. It says that there is a probability of hit at any level of hierarchy. So if I have to use the timing of my L1 cache, so first thing is that data should be available in my L1 cache. So probability of a data being in my L1 cache into time to get that thing from the L1 cache. Plus probability of miss, which would be typically 1 minus p hit, into time that I will take to get it from the next level of hierarchy. Are you getting it? So this is what I will get at L1 cache. At L2 cache also, suppose I have placed the request. Now, there was a miss at the L1 cache. So I placed the request at the L2 cache. Again, the same rule will apply. Probability that the data is available in the L2 cache into time to get that data from L2 cache to my controller, to my L1 cache. Are you getting it? And probability of miss into time to get it from the main memory. If there is no L3 cache, otherwise if there is an L3 cache, then time to get it from an L3 cache. Then the same principle applies on the L3 cache. So it's a recursive algorithm. Recursive, you understand? All of you? Itna to. So it is a recursive algorithm. It's like an embedded nested loop. Until you get the required data, you will go for the miss and bring that thing. Okay? So P hit plus P miss is always 100%. Either data is there or not there. Okay? So if you have the P hit available, you can always identify what the P miss is. Time hit should be made available to you, and then time miss you may need to calculate depending on the hierarchy of your cache subsystem there. So let's take an example. Memory has one cycle access if there is a hit, and it has 100 cycles access if there is a miss. If the hit rate of the cache is 97%, that is P hit is 0.97, what is the access time? लोग इशारा कर रहे हैं, सर नेक्स्ट स्लाइड आप अपना बटन दबा दो, आ जाएगा आंसर. मुझे पता है आंसर आ जाएगा. I still want you to solve it. आंसर तो स्लाइड में है ही. No? T hit can be different for different levels of cache. L1 cache के लिए T hit will be 1 cycles. यहाँ पे अभी जैसे आप देखो हमने L2 cache रखा ही नहीं, तो मेन मेमोरी रखा. मेन मेमोरी को एक्सेस करने के लिए 100 cycles लग रही हैं. It can happen that L2 cache के लिए आप कहो कि T hit is 8 cycles. आप उसको प्रोबेबिलिस्ट. सो यू विल यूज द वेटिंग. कभी भी आपको अगर एवरेज निकालना होता है, अगर आपको रेगुलर एवरेज निकालना है दो नंबर्स का, तो आप a प्लस बी बाय 2 कर देते हो. लेकिन अगर आपको वेटेड एवरेज लगाना होता है, तो आप W1 इंटू ए प्लस W2 इंटू बी अपॉन W1 प्लस W2 करते हो, है ना? सो दैट इज हाउ इट वर्क्स. यू विल वेट अकॉर्डिंग टू पी हिट. अगर पी हिट है तो आपका हिट वाला एक्सेस टाइम लग रहा है, और अगर P miss है तो आपका miss वाला access time लग रहा है. And then that is how you arrive at the average access time. That's what we are doing over here.
You also add L to memory, then we would need to calculate the T miss for L2. Right?
Yes. So over here, then instead of 100, so यहाँ तो एक देखते हैं, शायद एक और एग्जाम्पल है. मेरे से ज्यादा आपको पता होगा, आपने वीडियो देखा है. नहीं है. सो एग्जाम में तो आए हुए हैं, आपको पता है. इतना देखा होगा, नहीं देखा अभी. ओहो सर, अब प्रीवियस ईयर देखने का फायदा क्या? आपने तो हमारा दिल ही तोड़ दिया. हम इतना प्रीवियस ईयर करके गए थे, अब तो क्या फायदा? नहीं, प्रीवियस ईयर करने का फिर भी फायदा है, टू गिव यू द प्रैक्टिस दैट यू नीड. बट सपोज आई कुड से दैट T hit is 1 cycle, T hit is 0.97, let us say. Now T hit L2 is, let us say, 0.99, and T hit nahi, P hit. T hit L2 is equal to 8 cycles, and T miss L2 is equal to 100 cycles. Calculate करो इसका. So you'll first need to calculate the access time from L2 cache, because it's a recursive algorithm. सबसे पहले आपको सबसे हायर लेवल ऑफ मेमोरी का एक्सेस टाइम निकालना होगा, तो इसको आप टीएमएस की तरह यूज करोगे in the other levels. Do you see the difference? Even though my L2 cache access has 8 cycles, just because I introduced L2 cache, my access time reduced from 3.97 to 1.23. That is why we are going to different, additional levels of hierarchy, because this is the kind of gain that you start to see. Now you can play with these numbers of p hit for L1 cache and L2 cache and arrive at different kinds of combinations. How many of you have used that tool called GEM tool, GEM 5? So computer architecture जिन्होंने करा उन्होंने तो करा ही होगा. That helps you model all of this like this. Hmm? No. That is why I said if you play around with the T hit and the T miss, it may change. What happens is that as you grow to the next level of hierarchy, the probability of hit would actually increase only because the next level of hierarchy is larger. So you'll usually see an improvement. How much improvement is what is dicey. अभी हमने देखा कि ऑलमोस्ट 1/3 हो गया, 1/3 से भी कम हो गया, 4 से 1.23 हो गया. Is that okay? आगे बढ़े? Is this concept clear? So this is one of the most common numericals you will get on this particular thing. This kind of numerical, the most common numericals you will get in any exam. आप gate दोगे, कहीं भी दोगे, तो this is the kind of things you will get. Okay. Then capacity. Usually we think that bigger is better. Why bigger is better? Because my P hit will improve. The probability of hit will improve if I have more number of words available. But what we need to realize is that as the memory size grows, the T hit goes for a toss because the memory RC increases. So there's a sweet spot. You may want to say that if I have this much size of my L2 cache or L1 cache, that's the sweet spot. So you always have to be careful about what do you want to do. Then, is this point clear? This is fair. अभी हमने पहले भी यही चीज discuss करी थी when we were talking about scaling की need क्यों आ रही है. This point clear? Then another thing is line length. See, when you are accessing some information from main memory, it's going to take hundreds of cycles. Now we know that there is a locality of reference that exists. So अभी मैं एक word लेकर आ रहा हूँ, उसके बाद मुझे उसके next word को लाना पड़ेगा, फिर उसके next word को लाना पड़ेगा, and every time I can't wait for 100 cycles. So what I say is that when I'm fetching data from the next higher level of hierarchy into my L1 cache or wherever, then I will not just get one word. I will get a large number of words in one go. Why? Because anyway मुझे चाहिए. अभी नहीं तो बाद में चाहिए ही. Because of locality of reference. See, the entire tenet of cache subsystem is locality of reference. So I know that मुझे चाहिए होगा. Or that is the basic assumption on which I am operating. So what I do is, instead of getting just one word, I get a large number of words. So the total number of words I am getting is called line length. Is that okay? इसी को हम block भी कहते हैं. And the basic tenet is that there is a spatial locality in anything that I need to fetch from the main memory. Is this point clear? Now, what is the benefit of getting a large chunk of words? Because what you could do is that in the main memory, you could read 256 words in one go and start to transmit their data one after the other without waiting for the next clock to come. Or without waiting for the next instruction to come and not needing the decode and everything. तो आपने बहुत सारा डेटा एक बार में रीड करा DRAM से, अब आप उसको बस अपने इंटर फेस की स्पीड के ऊपर मूव कर सकते हो प्रोसेसर के पास. सो योर fetch time, or let us say tmiss, starts to improve, where fetch time is now first word ka access karne ka time, which could be very long, and then line length by fetch width, how many words did I want to get, into t subsequent. And t subsequent could be actually a very small fraction of the first access. Is that okay? But the first access agar 100 nanoseconds le raha hai, to subsequent accesses could actually be done in 2 nanoseconds. That huge a difference, because now you don't need to go inside the memory to get the remaining bit words. All of them are now available in the local, again, cache for the DRAM. So DRAM के end पे आप एक register file रख देते हो, and उस register file में आप सारे 256 words एक साथ रख लेते हो. Then you just need to fetch those words out from the register file there, which is much, much faster. Okay? So, and this you do at all levels. Even for a L2 cache, you could say that it takes 8 cycles to get something from L2 cache. Let me get at least 4 words in one go, or let me get 8 words in one go. So then you don't need to see any misses at all. Yeah, you had a question. So he's asking that cache size is limited. So should I get all the blocks? So that is where you will just in a little while see that there is a trade-off. If I increase the line length, obviously I improve the access time. But the challenge is that now I have brought in, suppose L2 cache, say I brought in 8 words in one go. L1 cache only had 256 words. Now 8 are gone. If I had brought just one word, I would have just used one. But now 8 are gone in one go. So line length means that in larger line length means that lesser number of or fewer number of independent blocks can be fetched. That means a kind of a top limit on number of applications that you can run in parallel. Are you getting it? So, T first is for first word of that line. In the DRAM, internally in the DRAM. But they don't come directly because your bus width cannot be 256 words wide. From your DRAM chip to your processor chip, you only have 1 byte, 8 bits wide bus. So words will, only 8 bits or 32 bits, whatever is the width of the bus, only that many bits can come in one go. So the first आपका transfer हो रहा है, that is one speed. Subsequent words are at a different speed. Because subsequent words don't need to go inside the DRAM. They will directly operate at the controller level. Are you getting it?
So that's also because of burst transfer, right? You only pass the address for the first word.
Yeah, this is also called as burst access. No, wait. We'll talk about burst access later when we talk about DRAMs. But this is perceived as burst by the L1 cache. Okay? Burst is not exactly the same thing. In DRAMs, you're actually reading only one word, which is 256 byte. It is not burst access. But it is perceived as burst access by the lower levels of hierarchy. तो burst word अभी बच्चों का मतलब बाकी लोगों को पता नहीं है, तो we'll look at burst a little later.
It will be sequentially or parallelly? Each bit of the word.
So, depending on the size of my bus, if my bus is 32 bits wide, I can get 32 bits in one go, at most. If my one word is 32 bits, then one word is coming in parallel, or all the bits of one word are coming in parallel. It may happen that my one word is 32 bits, but my bus size is only 8 bits. That's a bad system design, but it can happen. In which case, even to get one word, I have to have 4 cycles.
But size of bus we can limit up to the size of cache.
I didn't get this suggestion. What did you mean to say? What did you mean to suggest?
Size of bus is we can maximize up to the size of cache so that we can parallelly maximum fetch
So which cache? Will you maximize? Will you
like
L1 cache? So yes, the processor is 32-bit. You may say I have a 32-bit bus. In which case, one word will come in one go. That's it. That is what I said. If that is what is desired. If there are IO limitations, you may end up, because it depends on cost. Every extra pin is a cost. So if there are limitations around those, then it may happen that even though your bit width, the L1 cache is 32, you're able to get only 8 bits from the main memory. It could happen. We don't usually design it like that, but it could. Someone could do that kind of a design because of some other constraints. Not the constraint for them may not be performance. The constraint for them may be cost. Okay. See, the number of pins that you have to solder, that is a cost. Because first, उतनी सारा आपको IO pads and उतनी सारी pins आपको बनानी पड़ेंगी. That is manufacturing cost. But also, when you need to solder, you will need to solder as many pins. So even at the time of assembly, it's higher cost. So there could be applications which want minimum number of pins, therefore very high speed transfer may not be possible. If performance is not a premium, then you could do that. Is that okay?
So lastly, could you also explain what was the trade-off when we increase line length? Why can't we have very high length?
We'll come to that. We'll just come to that. But is the benefit of line length clear? We'll come to the limit of line length just now. If you have very large line length, then the total number of lines that you could store in a particular capacity of a memory would get limited. So the probability of miss will start to increase. Are you able to see this? If my line length is small, if my line size is, let us say, 4 bytes, and I have a small memory, 1 kilobit, I have a fairly low miss rate. But if in the same small memory, I use a large line length. Okay, you see how the miss rate goes up? Because छोटी सी memory अब एक ही line आ पा रही है उसमें. And your next program wanted a different line. So now there is a miss. Third program wanted a different line. Now there is a miss. So if the line length is very, very large, the number of lines you can store in your cache will reduce. That leads to more misses. So there is a sweet spot. Line length has to be decided in conjunction with the size of your L1 cache. अगर आपका कैश का साइज छोटा है तो आप बहुत बड़ी लाइन लेंथ नहीं रख सकते. Because then the total number of lines you can store will reduce. Is this point clear? It's something like this. Let's think about a chemist. एक chemist के पास thousands of prescription medication पड़ा होगा. Thousands of prescription medication in any chemist shop. But if this is the season of viral fever, majority people are asking which medication? Vicodil, कौन सी होती है? Dolo and Crocin and all this. Now someone will also need some medication for, let us say, stomach ulcers, but those conditions are rare. And if they happen, I will go into the back of my shop and pull out that medication. But if I have to go to the back of my shop for every medication, whether it is Dolo or Crocin or something, that doesn't work. So let us say I can keep only 8 medicines on my counter versus I can keep 20, 16 medicines on my counter versus I can keep 128 medicines on my counter. In which case will I have to make more trips in the rear of my shop? When there are only 8 buckets I have, then the probability that I will have to go back in the rear of my shop is higher. The same thing is applying here. If the number of lines that I can store in my cache is fewer, then when new requests come, I may need to go to the L2 cache again. But if the number of lines that I can store is larger, I can handle most of my requests here and my miss rate will be low. Are you able to see this? Is this point clear? Why we don't want very large line lengths? Because large line lengths means number of baskets or number of buckets I have at the counter is reduced. ठीक है? आगे बढ़े? I'm sorry? Why is it increasing after? So when I have a line size of 256, यही तो बता रहे हैं, when you have a line size of 256, then the number of lines that I can keep in that 1 KB is only 4. Therefore, the misses increase. But if I have a line size of only 4, even then the misses are higher because I am not really utilizing the principle of locality well. There is a sweet spot where I have to use the locality principle and still have a large number of lines available to me on my cache, on my counter. Is that okay? It's something like कि आपका जो basket है उसमें आप how many strips of Dolo can you keep? You just keep 1 strip of Dolo, then after the first customer, the second customer, you have to again go back. So that is the locality principle. How many adjacent words are you carrying?
Smaller number of blocks there.
Yes. Then hit rate isn't everything. We have to design our line length also carefully so that our overall TMS does not go very large. Okay. So this is again a different one on block size and locality. Over here, as the block size increases, the miss penalty increases because you have to fetch a larger line. Okay. As the block size increases, even though initially, due to benefit of spatial locality, I stand to gain excess time, later I start to lose because fewer lines can be stored. And that is where my excess time also starts to increase. Is that okay? This is exactly the same discussion that we just had. Hmm. No. It is saying that the first fall of miss rate from the highest miss rate to the lower one is because it is exploiting spatial locality. Spatial locality का benefit मिल रहा है when you start to increase the line size. Okay, that is what it means. But after some time, that benefit kind of gets eroded because now you start to have misses again because the number of lines that you have is fewer. Is that okay?
Exploitation of spatial locality is not for It is not shown for smaller block size, but it is shown just if we are increasing, then it is.
Yes. For very small block sizes, because you're just copied 4 words. You need a spatial locality of, let us say, 8 words. So the hit miss rate is more. After every 4 words, there is going to be a miss. If you had a line size of 8, after every 8 words, there is going to be a miss. If you have a line size of 16, after every 16 words, there is going to be a miss. The miss rate reduces significantly as you increase the line size. But you cannot keep on increasing it infinitely, because then the total number of lines that you can store gets limited. So the miss rate starts to increase again. Is this clear? Everyone?
What's the time required to fetch the entire block? Like suppose if it goes to cache and if not found, then it goes to memory.
Miss penalty, you may say, is T miss of the hierarchy. The time that you need to get the entire line from main memory into your L3 cache, that is T miss. Okay, that is the miss penalty. So we already also discussed about the direct mapped caches, where what we do is that, let me use the marker or highlight laser point over here. So see, this byte is the data that you wanted to store, the small one. Remaining everything is the address, which we have broken into tag, index, block, etc. based on where they're organized, how they're organized. ठीक है? So एक छोटे से डेटा के साथ, this is the data that you're talking about, उसके साथ tag रहता है बहुत बड़ा सा, and then you have one additional bit which is called as valid bit. So अभी जब हम coherency की बात कर रहे थे, when you're talking about coherency just a little while back, this was what we were talking about. Suppose my same data is available in adjacent cores. There are multiple processors using the same L2 cache. Processor A had fetched data of a particular location. Processor B also fetches data from a particular for the same location. Both had not updated the data until now. Let us say processor B now updates the data. As soon as B updates the data, the controller, the memory controller of the subsystem, will need to update the valid bit. It will at once say that the data in the L2 cache is no longer valid. The data in processor A is also no longer valid. So even if there is a hit in processor A, because the data is invalid, it will be considered as a miss. You need to go back to the L2 cache, get the data from there, and you will see, oh, data in L2 cache is also not valid. Then it will go to the processor where there is valid data, get the data from there, written into the L2 cache, and taken to the other processor. So are you realizing that as first thing, we moved at a different level of hierarchy, a different level of abstraction than circuit design now. We're no longer talking about transistors, and we're no longer talking about RC delays per se. We are talking about it in terms of total delay of a line access, but not exactly in terms of RC and transistors. And as soon as you go to the system level, जहाँ पे हमने memory के अंदर कहा there is a very complex control generation, control circuitry. Last time we looked at the example of clock generation circuit and the logic around it. We are saying that memory के ऊपर भी वैसे ही complex control circuitry चाहिए. इतनी complex कि DRAM से data लाने के लिए co-processors लगते हैं, and in fact इस memory management के लिए एक अलग controller लगता है. Are you able to see this? So this is not कि आपने 3 memories लगा दी अब हो गया. There are a lot of constraints that come around them. And if you understand memory design and system design both, this is a sweet spot to get these kind of job roles. Many people understand only circuit design. Many people understand only computer architecture. But those who understand both, they enjoy in this sweet spot. Because you can now make best of the optimizations that are required. Are you able to see this? So, does the tag match? If the tag matches, we call it as a hit. If it doesn't match, we call it a miss. Ouch. We have exceeded our time. We started late, but I still thought that we should be finishing on time. Okay, we will continue from here in the next class. Those of you who have not watched the lecture, I would recommend that please finish the cache thing. Next class, we'll also start with DRAMs. So you can also start to look at DRAM wala aspect. All the best.